Okay, so my name is Meredith. I am a physicist by education and by training, but for the past year I've been doing research in a chemistry group, which has been challenging but really fun and really satisfying. So for my talk, I'll be using physics and chemistry to talk to you about chemicals in space. So let's go through a few basic scientific questions, right? When we bring up space, the first question we think of is, what's out there, right? And once we figure out what's out there, planets, nebula, stars, what are they made of? And how were they made? And then we can take that one step further and point it towards ourselves. How were we made? How did life start on Earth? And if life started on Earth, couldn't it have started somewhere else? But before we can even ask this question, assuming there even is life, how will we find it? I'm not actually going to answer that question, but my research is very related, and people who want to answer this question want to know about my research. So physics will answer the question, how do we look for it? How do we take advantage of the laws of physics and how light works to look deeper and deeper into space with more accuracy? But chemistry and biology are really what tell us what to look for. What is life, and how will we know it when we see it? But this is about chemicals in space, right? So let's take this basic question and ask, how are chemicals in space made? So Ruby talked a little bit about the early universe. So there are protons and electrons, really fundamental building blocks of matter. And in the early universe, they were all just kind of floating around next to each other, single, ready to mingle. And then, when a proton and an electron love each other very much, they come together, bond, and form hydrogen. The most basic of all elements, so basic and so easy to make that, like Ruby said, it makes up 75% of all matter in the universe. And on the periodic table, it is number 1. So obviously not everything in the universe is hydrogen. So how did we start at the very early universe with hydrogen and get all the other elements? So if we look at hydrogen in space, we can throw another hydrogen on it. It actually really likes existing this way as a pair. We could knock an electron off, make it H2+, add another hydrogen, add a carbon, take off an H2, blah, 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 blah. Oh, look. So CH4 is actually something really recognizable here on Earth. It's methane, which is of great interest to astrobiologists, which is astronomers who are really interested in biology that's not happening on Earth. And we can actually make more chemicals from here and here and here. We can make a whole family tree of chemicals. And we've seen a lot of them. The ones marked in blue are the ones that we've detected from telescopes here on Earth. You'll notice that even though we haven't seen many of the black ones, they're sort of implied by their descendants, their grandchildren, so to speak. But let's just look at the trunk of the family tree for now. You might be asking, why all this hullabaloo? Why can't I just take 2 H2s to make an H4 and throw a carbon on it and call it a day? But the reason is because chemistry is a really, really complicated game of chess. Really complicated. Not only do all the pieces have their own rules about what they like to do, you can combine pieces to make new pieces that have new rules, and combine those combinations of pieces to make new combinations that have new rules. So asking why you can't move from here to here is kind of like asking if I had a knight on a chessboard and I wanted to move him 1 square to the right. If you didn't know the rules of chess, that would seem like a really easy thing to do. But actually, it takes 3 moves to move that knight there. So that's why we can't just skip from one end of the tree to the other end. But let's bring it down to Earth for a sec, talk more basic, and start with a chemical that everyone is very, very familiar with, dihydrogen monoxide, which sounds really chemically, but di means 2, so 2 hydrogens, and mono means 1, so 1 oxygen, which is H2O. So H2O, the chemical name for water, is based on what each unit of water is made of. So each unit of water, which is what we call a molecule, has 2 hydrogen atoms and 1 oxygen atom. So molecules are really, really, really small. In one drop of water, sorry, microphone issues. In one drop of water, there's about 1.5 sextillion molecules. That's one with 21 zeros after it. So they're really, really, really tiny. But going back up to space, stuff in space is really, really, really far away. The nearest galaxy, the Andromeda Galaxy, is 2.5 million light years away, which is a billion miles. So even light traveling as fast as it does, the light that is getting to us now left the galaxy before Homo sapiens existed. Humanity wasn't a thing. That's how far away it is. So we look out into space really, 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 really far away to find things that are so small we can barely see them on Earth with our strongest microscopes. So the question is, how do we see molecules in space? The secret is that molecules bounce. Every molecule bounces all the time, constantly. Every molecule in the chairs you're sitting in is bouncing. Every molecule in the stage is bouncing. In the air, in your drink, everything everywhere, always bouncing. So this picture makes it kind of look like they're balls on rods, but that's not really true. They're more like balls on springs. So for a water molecule, it can bounce like this, or maybe with a little more sachet in its step, or it can bend. And actually, it can do a combination of these things. So it can go out and in and out, and I practiced that, but it didn't really work. But so molecules can bounce a bunch of different ways, but the key is that every bouncing pattern is unique. Every molecule bounces in a unique way. So if we put a different combination of atoms in a different structure, it's going to bounce differently. So if we have our molecule, another important thing is that energy, when we're talking about things that are really, 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 really small, is quantized. So there are only certain values of energy that'll work. If I try to give this molecule energy, it'll only accept that energy if it's at a very precise value. But it's got a few of them, it's got a few values, because it's got a few bounces. Each bounce has a different amount of energy, and when a molecule accepts energy, it'll only accept amounts of energy that match its bounces. Before I move on, congratulations, you've all learned quantum mechanics. So, how does this help us detect molecules in space? So if we have our molecule and we have the energies that it will accept, matching its bounces, if light hits the molecule, light at low energies through high energies, and we measure what light comes back out at the end, we'll find that specific energies of light are missing. They were absorbed because they match the energy of the bounce. So each line corresponds to different bounces or combination of bounces, and we call that a spectrum. So this spectrum is unique for every molecule because this spectrum corresponds to the bouncing pattern that is unique for every molecule. So it's like a fingerprint, or aesthetically it maybe looks a little more like a barcode. And we call this absorption spectroscopy because we get a spectrum from seeing what light was absorbed. So we have light from space. Typically we're looking in one place, at one star, one nebula, and we see what light is coming off of it. And that light is full of barcodes. So because we have studied chemicals in the lab and we understand how they bounce, we have sort of an encyclopedia of molecule barcodes, and we can go through them with a little barcode scanner, also known as math, and go through these barcodes and sort them out and say, oh, there's water on that planet, that sort of thing. So if we go back to our tree to methane, my pet molecule, my problem child, is CH5+, which, as you'll notice, is black. We have not seen it yet for reasons that you'll see. So it's the spectrum of CH4 methane. This is actually a real spectrum that was taken in a lab. And so it's just the spectrum we were looking at before on its side. The lines represent where light was absorbed, and the height of the line is basically how much it was absorbed. So you can see it looks pretty regular. It looks pretty even, looks really nice, and that's because CH4 is really symmetric. It looks really regular. It's easy to define. The spectrum for CH5+ looks like this. Not so much. It's nonsense, really, actually. And that's because when we look at how CH5+ moves, it moves a little like this, like it's made of jello, and that's really hard for us. That doesn't follow the rules that we're used to. Now, you might be asking, we have the spectrum, we have the barcode, it's right here, so why can't we use that to see it in space? And the reason is because it's not enough to know what the pattern is. We have to understand it. This pattern, even the pattern of CH4, can change depending on what conditions the molecule's in. It can change with temperature, it can change with pressure, it can change in the presence of other molecules. And we know exactly how every line in that spectrum is going to change based on that because we know what each line is for. We know what bounce corresponds to each line. Here we have no idea. So if we found CH5+ in space, we would never know it because our barcode detector couldn't pick it out among the rest of the barcodes. And that's a good principle of science, is that results don't mean much if you don't understand why they happened. So really, the encyclopedia, the title should have been Molecule Barcodes and Their Interpretations. So, how do we decipher the barcode of CH5+? When scientists don't understand something in real life, they do it on a computer. So that's what I do. I analyze CH5+ using math, physics, and computer programming. So my field is theoretical physical chemistry. The way that I'm doing it is sort of the unique part. So I'm using a technique called Monte Carlo, actually named after the Monaco casino. And one more click. So we are going to calculate the value of pi using Monte Carlo techniques. So if we have a circle and we put it in a square, exactly fitting it, then the area of the circle over the area of the square is pi over 4. I'll leave that exercise to you at home if you'd like to prove it. But here's why we use random chance to calculate pi. We'll throw down a bunch of dots into an area that matches the square. Totally random, I just drop them on the floor, see where they fall. But then the important part is that I'm going to tag them. I'm going to tag them blue or orange based on whether or not they are inside the circle. So once I do that, and I take the number in the circle over the number of the total, because all of them are inside the square, then I'll get pi over 4. Now, I already did this math for you, but that gives me a value of like 4.5, not quite 3.14. The secret to using random chance to give you the results that you want is you have to do it a lot. A lot. You would have to do this about 10,000 times to get the accuracy you wanted. So the simulation looks a little like this. So if we take the upper right-hand corner, we throw down the black dots, tag them, and then they stay there. We keep accumulating results, right? And it slowly fills in the circle and the square, and you can see that the value of pi is getting closer and closer to 3.14. I actually think it overshoots it at some point, but this was only about, I think, 25 times. So, need a lot of data, need a lot of computing power. And we can do Monte Carlo with molecules. So it's a little more complicated, involves a little more quantum mechanics, but the basics is that our random points that we throw down and see where they fall are like random snapshots of the molecule in certain positions, in certain states, at certain energies, etc. So we take our random snapshots and we tag them based on what information we want. So in our case, we want to know if they are lowering the energy or not. Because eventually we're going to use energy differences to try and, devolve the spectrum. But we use that to find the most important configurations. So what do the configurations that the molecules prefer tell us about the bouncing pattern? And then the cool thing about theoretical work is that I can also play with reality. So I can switch a hydrogen for something else, or I can change the temperature, or do a bunch of things just to test it, just to see what happens. And that can give us a lot of insight as to the nature of the molecule. So, using a combination of quantum mechanics, Monte Carlo techniques, physics, and chemistry, we can bring a new understanding of weird floppy molecules like CH5+. find it in space, and solidify our knowledge of important chemicals for biological life and how they're made in our universe. I'd like to thank my research group, the McCoy group in the Department of Chemistry at UW, Engage for their awesome course, Seattle Town Hall for giving me the opportunity to speak, and the NSF Graduate Research Fellowship Program for funding my research. I'll now take any questions you might have.